We can now take a closer look at the different types of bonding that exist in solid materials, including both the three types of primary bonding that we've already mentioned, as well as secondary bonding that exists in molecular compounds. Again, with primary bonding, there are really three types: metallic, covalent, and ionic. Metallic, whenever we have metal elements bonded together; covalent, when we have non-metal elements bonded together; and ionic, whenever we have a metal paired up with a non-metal. We can also imagine situations in which we don't neatly fall into one of those three categories, but lie somewhere in between, something we might classify as mixed bonding. And one example scenario you might think of is those of the metalloids, where the elements themselves are neither metals nor nonmetals, but rather lie somewhere in between. Let's take a look at metallic bonding. Again, remember here we have all atoms that have relatively weak grips on their electrons due to low effective nuclear charges. As a result, the valence electrons are held very loosely and are relatively mobile. We tend to think of metals as having a sea of donated valence electrons. This gives rise to the nature of bonding and properties in those materials. The bonding is non-directional, and as a result, crystal structures of metals tend to involve simply packing atoms as densely as possible, like packing oranges in a box, without much regard to the angles between those different spheres. Because of the delocalized nature of the electrons that are free to roam around among those atoms, helps to explain the good electrical and thermal conductivity that we see in metals, as well as the ductility and malleability of those solid materials, since the atoms are relatively free to slide past each other. It's important to emphasize that in metals there are no molecules. Rather, there are enormous numbers of atoms, uncountable numbers of atoms, packed together in regular arrangements, crystal structures. Ionic bonding, on the other hand, again involves a metal and a non-metal. The metal having a weak grip on its valence electron, or low effective nuclear charge, and the non-metal having a high effective nuclear charge, or strong attraction for electrons. As a result, the non-metal attracts an electron away from the metal atom, causing an electron transfer and net charges on each of the atoms. The metal, because it's lost an electron, now has a net positive charge. The non-metal, because it's gained an electron, has a net negative charge. As a result, we can now think of these two atoms as simply being charged spheres with positive and negative charges. This type of simplified model for bonding allows us to use mathematical models from physics for positive and negative attractions to describe this type of bonding. Again, the bonding is fairly non-directional. We're just packing charged spheres together. But in this case, the bonding is very localized, since the electrons in both atoms are held strongly. Remember that the electrons in the metal atom are now only the core electrons, since the valence electrons have been stripped away, and while those in the non-metal atom are held strongly because of its effective nuclear charge. As a result, because the electrons are not free to move about, these materials tend to have poor electrical conductivity and poor thermal conductivity. They also tend to be quite brittle, since the atoms cannot move past each other easily. As with metals, there are no molecules in the case of ionic materials, but rather enormous arrays of uncountable numbers of these ions packed together in some regular crystalline arrangement. The third type of primary bonding, covalent bonding, which we see within the chains of polymers and also within a number of semiconductors and ceramic materials, involves nonmetal atoms that are sharing electrons. Again, in this case, both types of atoms have strong effective nuclear charges and therefore strong grip on their valence electrons. As a result, neither donates the electron to the other, but rather they share those valence electrons in order to fill their outer shells. If you remember, and which we'll review shortly, the bonding in these nonmetal systems, covalent bonding, is highly directional in its nature. Whenever we have three or more atoms, there are predictable angles between those bonds that are governed by hybridization theory. Angles of 180, 120, 109.5 degrees, and so on. Because there are only nonmetal atoms present, the bonding is quite localized between those atoms, and so we see very poor electrical conductivity and poor thermal conductivity in most covalently bonded materials. Unlike the other two types of primary bonding that we saw, it is possible in the case of covalent bonding to have molecules, that is, discrete packages of small number of atoms that are covalently bonded together. But it's also possible in some cases to have large networks of enormous numbers of atoms that are all bonded together through these strong covalent bonds. Examples being things like silicon dioxide, diamond, silicon carbide, and so forth. In reality, most substances fall somewhere on the spectrum between ionic and covalent bonding. At one extreme, we could have something like cesium fluoride that is almost purely ionic bonding, having an element with very low electronegativity paired up with one with very high electronegativity. At the far end of the other spectrum, we might have something like a fluorine-fluorine bond, where both atoms in the bond pull equally on the electrons. But of course, in between, we could have a wide range, such as magnesium oxide, which we would generally think of as an ionic bond, but not as ionic as cesium fluoride. We could have something like zinc sulfide that falls somewhere in the middle between ionic and covalent bonding. And we could have a bond like carbon to chlorine that we certainly think of as a covalent bond, but where the two atoms do not pull equally, the chlorine pulling slightly more strongly, and so we think of this as a polar covalent bond. So in reality, there is not really ionic or covalent bonding, but rather a spectrum from ionic to covalent bonding, and most ceramic materials fall somewhere along this spectrum. Chemists often try to quantify where in the spectrum we are by calculating a percent or fraction ionic character for a bond, using the electronegativity difference between the two atoms in the bond. For example, if we wanted to calculate the percent ionic character of a magnesium oxide bond, we could look up the electronegativity for each of these elements, 1.2 for magnesium, 3.5 for oxygen, and we could calculate their electronegativity difference, often represented as delta X. And in this case, the electronegativity difference would be 2.3. As indicated in the equation above, we can then calculate the percent ionic character in the bond by taking 1 minus the exponent of negative 0.25 times the electronegativity difference of 2.3 squared, and then of course converting this to a percentage. So we then get a value of 0.73, or in other words, 73% ionic, 27% covalent. So primarily ionic bonding, but with a slight covalent character. For an even more general look at all of the different types of bonding and the mixed bonding characteristics they can have, material scientists sometimes talk in terms of a primary bonding triangle. Here we can actually make a graph with average electronegativity on one axis and difference in electronegativity on the other axis, and create a graph, if you will, using this triangle of ionic, covalent, and metallic bonding. At one extreme, you could have cesium, where in cesium metal there is of course no difference in electronegativity. All of the atoms are the same, so the difference in electronegativity is 0. The average electronegativity is the lowest of all possible elements at 0.7, and so this corner of the triangle corresponds to cesium. At the covalent corner of the triangle, we have fluorine, F2, where again the difference in electronegativity is 0 since the atoms are the same, and the average electronegativity is the maximum possible, 4.0, for fluorine. And then finally on the third corner of the triangle we have the compound cesium fluoride, where the difference in electronegativity is the maximum possible, 3.3, and the average electronegativity falls exactly in between the two values shown, so 2.35. All other possible bonds between elements on the periodic table will fall somewhere within this triangle, and so we can get some sense of how close any particular bond is to ionic, covalent, or metallic character, or where in between those extreme categories a particular bond lies.